A very good afternoon to all of you. I was asked to talk on two aspects. One was what the climate change has for Ganga. And then the second part of the question was, is Ganga climate ready? So I'll try to use some of our existing work. For example, the recent work, though we had done the climate change impact assessment on all the river basins of the country, which went as the national communication, the phase 1 and phase 2. But this is something recent which we did using all the recent scenarios, the RCPs. And this was done as a part of the European Union collaborative project, where the question was raised to find out what will be the difference in having warming level stabilized at 1.5 degrees, 2 degrees, 4 degrees, and so on. I'd like to mix the second question also along with this. We'll look at the climate change implications in Ganga. But the second part is equally important, that are we ready to take care of the climate change implications? There I feel that this question should not be talked in isolation. We have to first talk in terms of, are we managing our natural variability of water resources appropriately as of now within the present variability? And the climate change is only going to aggravate that variability slightly to a different extent. So yesterday also I was sharing with the people in the small group, where I was sharing that what was our contribution to the Ganga River Basin Management Plan, where we tried to simulate the hydrology, including the groundwater of this basin, and try to understand where we are, what we are doing to the resource. And this was done using a modeling approach. We used the hydrological models and the groundwater models in conjunction. Now, the hydrological model does what it does. It mimics the natural processes in a mathematical formulation. And you try to generate what the nature is doing. And that is in terms of when the rain or the precipitation falls on the landmass, where it will go, what will happen to it, how much will go into the soil and get stored there, how much will flow over the surface, how much will be the deep percolation and it will join the groundwater table. All those processes are governed by 4 elements. One is the terrain, the other one is the soil properties, along with the profile, how the soil properties change from the top soil to the lower level. It also depends on the land use, what kind of land use you have, whether what kind of vegetation is there, if it's forest areas, if you're doing the agriculture, what kind of crops you are growing. They can be barren land, they can be urban areas. All those are part of the land usage. And then you need to impose what is the nature is doing in terms of the weather conditions. What was the temperature on a particular day? How much precipitation it received? What was the minimum temperature, maximum temperature, the relative humidity, the wind velocity? All these are parameters which go into the modeling to analyze from the natural processes that simulates the natural processes. So there, you can generate now for smaller areas. We divided the whole Ganga into very, very small areas, around 1,000 sub-areas. And then for each one, you can see here that on the left-hand side is the annual precipitation. So that itself is variable over the whole Ganga basin. Then the consequent to the precipitation is that how much water yield you obtained from the land mass. And that is again is dependent on the precipitation, but is not directly dependent, is not linearly interpolatable. You also get from the modeling the actual evapotranspiration because it has the crop growth component, and you can simulate different crops using its phenological parameters, and you can also go to the extent of finding out how much is the yield going to be as per the natural precipitation. So in this particular case, since we are dealing with a basin which is not only having the natural precipitation, for the crop production we are also using irrigation. So when the irrigation was put onto the landmass, that is also taken into account. So all the reservoirs are simulated. And what was being mentioned here, that now we know that how much is the water used for irrigation and how it gets translated into the atmosphere, and how much is the actual evapotranspiration versus the under the irrigated conditions and under rain-fed conditions. All that comes out as the outcome. You can also find out how much is the groundwater discharge as per the actual precipitation. Also, along with that, how much was the groundwater recharge on account of your irrigation. So this is something which is validated, and once you validate that and you get similar flows where you are observing the flows. So we were given by the Central Water Commission around 250 locations where we had the flow series for the last 50 years. We compared what we are getting the flow from the data at the observational points and how much is the model giving the flow. They were quite reasonably comparable. Now that gives you additional information, and that is the use, very big use of the modeling approach, that now for all the locations which can be tens of thousands, you can get how much is the flow which is available at that location even if you have not observed. You can also get as the outcome what is the soil moisture on a daily basis on account of your precipitation as well as on account of your irrigation, dumping of the water artificially. All that can be made use of in different ways to find out what is how the hydrology is functioning. And when we are looking at the climate change impact, this is what has to be used. There's no other way you can find the implication of the climate change. You have only available with you the climate change models output in the form of here we have the actual locations of rainfall where you are observing the rainfall, but in that case you have a grid. You have a grid which is at around 25 kilometer by 25 kilometer locations, points, where you get the forecasted values for the simulated values for the next 100 years. And that is what has been used, where you get what is the precipitation going to be on a daily basis for those 100 years, starting from now to end of the century, how much is the temperatures. All that, once you validate these models, then you can impose those projected conditions and get the implication of the climate change. But coming back to what we did during the exercise for river basin and the Ganga River Basin Management Plan, we wanted to know, because this was a question which is normally being debated, how much should be the environmental flow in each river stretch? Now, from where we will get how much it was before the development started. Now, that is what we could reproduce after using the data of the last 50 years and switching off all the dams, switching off all the diversions. We could find out that at that time, how much was the natural rainfall, okay? How much was the recharge taking place? And at that time, how much was the groundwater table, how much it should have been? That is what you can see on the lower two panels, where the pre-monsoon and the post-monsoon groundwater tables have been simulated, and these are the water levels which we should aspire for. These are the water tables which make the river perennial, all the stretches perennial, because that is the water which also flows in the lateral direction toward the river and contributes to it, makes it perennial. Similarly, the upper one is the present condition. So we could get that simulated indirectly by putting all the pumping of the water which is happening. We could use the hydrological, the groundwater model, and we could simulate that how much is the present condition. So that was kind of a validation also. And this has been published in the Journal of Hydrology. We could also find out that because of our actions, because of our over-mining of the groundwater, which are the stretches of the river of Ganga which are now losing water to the groundwater, which is something which is unnatural, which is not something part of the natural process. And since on all these stretches you can see in the yellow and the red, they are the ones where the loss of groundwater is happening. And we could identify and quantify the whole thing. Now coming to why I'm bringing that question, I think all of us are very, very keen in finding solutions and not keep on debating what we have been doing for many, many years. Now the solution lies in ensuring that your water use in the system of Ganga basin is within the availability, well within the availability, and presently is not, and that is evident from the fact that your the groundwater table is falling down. That means that there is a deficit which is coming out of the groundwater abstraction. Now what we need to do is to take these smaller areas, the smaller basins, you can call them watersheds, and do the water balance in each one of them. Try to bring all those players, all those programs which are working on the water, the common resource, and make the local decision makers, the local managers, because all these planning processes are done at the district level. So the hydrology and the administration, normally we say that we shouldn't divide them, but we can always find correspondence. We can find out how much is the water which is falling in a particular district and how much is the total demand which they have imposed. How much of the irrigation water is being used, how much is the industrial, how much is the domestic. And once you put that together, you will immediately know that your demand is much more than what the availability, what the nature is giving you. The main requirement at this stage in not only Ganga basin, every basin, is to bring your demand within the availability. Now, we have to find ways and means, and the easiest possible way there are many ways, but the easiest possible way is to enhance your efficiency of irrigation, because 85% of water is being used for agriculture. Now, if you can take that from 30%, which is the present average efficiency of water use, to 60%, you have doubled the quantity of water. So the investment should go in there. All the government investments have to be directed, and then you have to find mechanism by which you can create evidences that has the groundwater table started coming up? Have you now the situation where your demand is less than the availability? If you do that, you can revive your system. So now we are at a stage where we need to revive the systems. And as part of our Ganga basin studies, we had given various options. We had also given through the simulation that if you change the cropping patterns, how much gain you will have. If you enhance the water use efficiency, how much gain you will have. And then we can take care of all the other issues of environmental flows. Because in environmental flow, if you are recovering almost the same amount of water which you are using for irrigation, why can't we give 20% of water back to the river and not allow that diversion? That diversion can be reduced. So you can revive those environmental flows easily if you are doing in a proper manner, if you are doing it in a scientific manner where you know that how much advantage has been already taken out and what is the evaluation of your actions. So far in our country we don't have, it's a pity that we don't have the habit of evaluating any of our actions. Whatever we do, we just walk away and feel that yes, we are done good, and there's no mechanism in place where we can actually create evidence that this was what was the gain, and that is in place. So we need to use the scientific mechanisms, including the observational mechanisms, that how we can observe. We need to legislate the groundwater abstraction, and it's many a time people say that how you can do that because it will be the farmer which will be the injured party. No, I feel that you have to ensure that by changing the method of irrigation, it's not the farmer who's going to hit. He will not be hit because it's proven your enhancement of efficiency of irrigation also increases your yields almost by 30%, 40%. It has been proven many times. So he will be happy. But the basic requirement is that the investments which we are making in a very, very arbitrary manner, it has to be systematically done. You have to ensure all aspects of that total cycle, that you have the amount of water which is regulated, and you have to also ensure that the demand is reduced. Then you can also talk in terms of the reuse. In industrial areas, in the urban areas, reuse is very easy. It's not very difficult, but nobody has tried. Nobody has the intent to do it. So if you take this water as a resource which is going to decline, and all of us know that is going to become more and more difficult to manage, is worth the investment which we are talking about. And I can prove that, I'm sure, because we have made the tools of various kinds where all this what I'm talking about, we have a site where we are giving the forecast, the flood forecast for the whole country, using the IMD data of 7 days forecast, which they are doing and disseminating. And we are using that data and also making the forecast. What is the flood forecast for any location in the country? Now, while doing that, we have all the other elements. What is the soil moisture? What is how much precipitation has fallen, and how much is the low flows? You can, through the modeling, you can find out many other aspects which I don't want to discuss here because it needs a lot of time. So coming back to the climate change implications, this is what we have done. We have used around 11 different models where you can see those points on the lower right corner are the points where the forecasted, the projections of RCM weather grids, the regional climate models projections are made. And that is the data which has been used. Along with that, we have also used all the existing structures where how much irrigation is being happening now. And in this, the major question was that what will be the situation like in this particular basin if it will be 1.5 degree increase, 2 degrees increase, 4 degrees increase, and 6 degrees increase. All these models, they are different models, different climate models, and they come out with different year when this will be achieved, when this will be, 2 degree will be in place. So you can see here that the first model, it says that 2034, it will have 1.5 degree increase, and 2 degrees 46, 4 degrees 85, and 6 degrees, it doesn't simulate. It doesn't have that 6 degree increase. So likewise, there are some models which are saying that that is in the next century, 21, 28, 6 degrees will be achieved, but those models have simulated beyond this century. All this was done, and then we tried to convert these conditions that under these specific warming levels will be the precipitation in the Ganga basin. And you can see that many of the models are talking of a similar thing. There are some models which are wavering. That first model on the top is giving a condition, or the last model in that segment is having some conditions which are different from the average conditions. But it was just to show that all these different models are not so different as far as the Indian conditions are concerned. And then we translated these into different outcomes, that what will be the impact on the runoff, what will be the impact on evapotranspiration, the groundwater, all those things were done. And ultimately, we also tried to convert that into indices. That what will be the index, because socioeconomic aspects are very important in terms of looking at the vulnerability on account of the climate change. So we brought out that data also and clubbed with the biophysical data and tried to come out with which are the parts of Ganga Basin which will be more having higher vulnerability. There is a lot of other analysis which has been done in terms of what will be the drought conditions, what will be the flood conditions, how much will be the implication on the low flows, how much will be the implication on the high flows. But in general, these are the things which you can find that there is definitely a reduction in the rainy days. The amount of water is not going to be less, but the number of rainy days are much lower. Now that has an implication. If the number of rainy days are reducing, the gap between the two rains is going to be more. So your rain-fed agriculture of 60% in the country is, and in the case of the Ganga Basin also is around 60% rain-fed agriculture, that's going to be affected. So you will find a situation where the crop might not be able to survive because of the less number of rainy days. Then similarly, the intensity of precipitation is going to be higher. So what you are getting now once in 50-year return period, it might be equivalent to once in 25 years. That is the kind of situation which is going to, and that we have already started seeing that the intensity of rainfall is much higher than what we have been getting all along earlier. More water demand because of the higher temperature, that is, of course, the agriculture demand will go up. So this is my last slide, that what you need to do, this is what I have already said, that you have to use the integrated water resources management tools in a proper manner, where you have to make sure that your demand is way below the availability. Whatever you do with the demand, you might have to legislate ultimately, but if you want to keep the hydrological health of your system, which will allow the rivers to really keep on performing the environmental functions which they have been performing, if you want them to really have a carrying capacity, even whatever small pollution is getting into them, that they should be in a position to take safely. And also the environmental health, which is in terms of the water quality as well as environmental aspects. And for additional coping strategies, we might have to perform the vulnerability assessment of the landmass and look at the prioritize, which are the areas which need priority and the priority some more focus. And those areas you have to talk in terms of looking at the various adaptation options, but keeping the sustainability into focus. Unless the option is sustainable, it can be a maladaptation. So we have to be, I think these are some of the things. If we use frameworks, and in all this, the knowledge frameworks, the knowledge base is going to play a major role. Unless you know what is happening, you cannot find solutions. Thank you much.